Hello, hello, hello. In this episode of a worked example, we're going to explore the concept of tangential acceleration, which has to do with the rate at which the speed of an object is changing. So here's the problem. We're going to consider a case of projectile motion near the Earth's surface. So we launch a projectile and we're going to assume that it undergoes a constant acceleration of magnitude 9.8 meters per second squared in the negative j hat direction, so straight down. And as you know, the particle is going to follow a some parabolic trajectory. And we're told that at some instant in time, the projectile has a velocity of 30 meters per second I hat plus 30 meters per second j hat. So it's apparently traveling at an upward 45-degree angle with respect to horizontal. And at that instant, we'd like to know what is the value of the tangential acceleration of the object. And by definition, what we mean by tangential acceleration is the rate at which the speed of the object is changing. That is dv dt, where v is the speed of the object. So is there enough information here to answer that question? And of course, the answer is yes. So let's see how this works. So the first thing to note is that this is a figure that's taken out of my edition of Wolfson showing projectile motion. And what we're plotting is at different points in time what the acceleration and the velocity of the projectile look like. And we're assuming, as in this problem, that the acceleration is constant, always straight down. So we see that that means that the x component of the velocity is going to remain unchanged throughout the motion, but the y component is going to change at each progressive time. You notice the y component is becoming more and more negative. And in our particular problem, we're considering an instant in which the object ends up having x and y components of equal magnitude. So apparently on this graph here, if you look at the way these vectors are drawn, the y component of this vector looks like it's still a little bit bigger than the x component. So we're talking about a point maybe somewhere right around here in which the velocity at this point is got equal magnitude x and y components, each of magnitude 30 meters per second. And we're asked at this point in time, can we figure out what the rate at which the particle's speed is changing? Well, to proceed, I'm going to remind you of something that we saw in the episode of What's the Big Idea about circular motion. But within that episode, we considered towards the end of that What's the Big Idea, we talked about the case of non-uniform circular motion in which an object was going around a circular path and changing speed. But I want to slightly generalize that discussion. There's nothing about this discussion that really requires that the object be going around a circle. Really, this discussion applies to object going around any sort of curved path. And a parabolic trajectory is certainly an example of a curved path. So the basic idea is that whenever you have an object moving along any curved trajectory, you can always separate the acceleration of the object into two perpendicular components. There's a component parallel to the motion, which we call a sub t, and that has to do with the rate at which the speed of the object is changing. And then the radial component of the acceleration, that is a measure of how much the acceleration is due to the fact that the direction of motion is changing. Now, in the present problem, we're interested in the tangential acceleration. So basically, what we want to find out is what is the component of the acceleration along the direction that lies tangent to the curve at the point under consideration. So here we're sort of zooming in on the situation. The velocity vector at this instant in time is headed upward without making an angle 45 degrees with respect to horizontal. The acceleration vector is pointed straight downward. And we can always break the acceleration into two components, one tangent to the parallel to the direction or anti-parallel to the direction of the velocity vector, and the other perpendicular to that direction. So as this figure shows here, the tangential acceleration is given by this, the magnitude of it is just equal to the length of this side of this right triangle here. This is a right triangle here. Let me make that clear. That's a right triangle. And AT, the tangential acceleration, is just given by the length of this side of the right triangle. The acceleration vector forms the hypotenuse of that right triangle. So now it's just a matter of some simple, very simple trigonometry. The magnitude of the tangential acceleration is just the length of the hypotenuse of that triangle, which is 9.8 meters per second squared, times, and we see that this angle here is a 45-degree angle, right? Because this is 45, this is 90, at least 45 degrees left over here. So that means we need a factor of cosine of 45 degrees here, or 9.8 meters per second squared times the square root of 2 over 2. And that works out to be about 6.9 meters per second squared. And I really have been a little bit sloppy here because I should have been putting in a minus sign here. Because, of course, at this point in the motion, the effect of gravity is to slow the object down. So the tangential acceleration is actually a negative number. So that means for at this instant in time, the speed is slowing down at a rate of negative 6.9 meters per second squared. So that's it for this worked example. Hope to see you again soon. Bye bye.